We've been talking about phase transformations, and of course we're all aware of the mundane ones like going from a solid to a liquid or liquid to a gas. But we've got a few interesting ones to talk about today as we wrap up our unit on phase transitions and phase equilibria. What I'd like to start with is element helium. Helium has two isotopes. Helium-4, which consists of 2 protons and 2 neutrons, and helium-3. Now, we'll start with helium-4. It's the more common isotope. Helium-3 is more rare. But helium-4 will certainly be a nice example of a transition where we not only have a solid, a liquid, and a gas, but we have 2 types of helium liquid. We call it helium-1, which is a normal liquid, and helium-2, which is a superfluid. And so we have a phase diagram that looks like this. You'll notice that helium will stay a liquid, is the only element we know that remains a liquid at 0 Kelvin. Should we be able to reach 0 Kelvin, which we can't, but it will remain a liquid unless you can raise the pressure to about 25.3 bar. Now, that's a pressure term that we haven't talked about very much. I'd like to just put it in more familiar terms. Conversions that we use, 1 bar is equal to 0.9862, 0.986,923 atmospheres, or 1 atmosphere is 1.013 bars, if you like. So that's the conversion factor you can use. So a bar and an atmosphere are fairly close. If you're used to working with atmospheres, so the bar is not that different in size. But at an atmospheric pressure, the boiling point is 4.2 kelvins for helium. You can see that right here. But you have critical points at 5.2 Kelvin. So the way this works is the following. 5.2 kelvins, 2.3 bar, helium goes from a superfluid to from a normal liquid to a superfluid. And so the superfluid has the following property. When I'm below 2.2 or so, we have 0 viscosity. So you can see videos of helium literally climbing up a beaker all by itself without any provocation. Because there is 0 viscosity left. It's a very interesting substance, very strange substance, but it's what we call a superfluid. As I say, it is the more common type of helium that we'll use. We will talk about superfluidity also when we talk about quantum statistics, which will be a couple of units from now. On the other hand, we have helium-3. Now, liquid helium-3 is much more rare. And to see superfluid properties in helium-3, you have to go down to a much, much lower temperature. It's on the order of millikelvins to reach a superfluid phase for helium-3. And in fact, there are 2, as it turns out, there are 2 superfluid phases for helium-3, but you've got to go below 3 millikelvins to reach them. So an example, so what's happening here when we talk about a phase transition in the case of helium-4 and helium-3, it is a case where we're going from a fluid, or normal fluid, to a superfluid. Another type of phase transition or phase transformation we want to talk about is the type 1 superconductor. Now, examples of this would be mercury, tin, and lead. And what happens if we have a case of a fairly low magnetic field and a very low temperature, for example, for lead, my critical temperature would be something like 7.2 kelvins. and a magnetic field of about 0.08 Tesla, lead will go from a normal substance to a superconducting substance. Now, a superconductor, as you probably know, is a substance that has zero resistance. So it is a perfect conductor of electricity. Good examples of that would be, in this type of superconductor would be, as I say, mercury, tin, and lead. We can study more about superconductivity in a condensed matter physics class. I hope that you'll get to do that at some point. Yet another type of phase transition that we talk about is ferromagnetism. An element like iron, for example, is ferromagnetic up to a critical temperature. In the case of iron, the critical temperature is 1043 kelvins, where iron goes from, down here it is a ferromagnetic, so a very strong magnetic field. In this case, the phases are either magnetized up or magnetized down. Once we go past this critical temperature, what we call the Curie temperature, in this case it's 1043 kelvins, iron goes from being ferromagnetic to paramagnetic. So this is another type of phase transition that is interesting to talk about. In a sense, this is a critical point. And perhaps the last type of phase transition is a very interesting phase transition between two types of carbon. Carbon has two phases. One is graphite and one is diamond. The normal phase of carbon is graphite, unless you go to fairly high pressures. So at ordinary pressures, your more stable phase is graphite. When I go to high temperature, it's easier to convert graphite to diamond, but what I really need to do it would be high pressures. One way that we can examine this is to look at the Gibbs free energies for diamond and graphite. The Gibbs free energy for diamond is higher than that of graphite by about 2,900 joules. So that's why graphite is the stable phase, particularly at room temperature. At higher pressures, though, we can look at the change in the Gibbs free energy as a function of pressure for this. And of course, that gives me a volume, so it tells me that a mole of graphite has a greater volume than a mole of diamond. So therefore, the Gibbs free energy of graphite will grow more rapidly as the pressure goes up, thus making it easier to form a diamond. Once you're above 15 kilobars, 15,000 bars, diamond is more stable than graphite is. So you have natural diamonds, in this case, forming at great depths in the earth. Pressure of 15 bars would require something on the order, or I should say a pressure of 15 kilobars would require a depth of about 50 kilometers before you would see graphite. So as you see, the higher the temperature, the more graphite is stable, which makes it greater. You have to go to even greater depths to make diamond more prevalent. So these are examples of phase transitions, something other and probably more interesting than things like boiling water or whatever the case may be. Now, having said that, at the very end, the very last unit of this course, we're going to study critical phenomena, which is to look at what exactly happens at these critical points. And probably all of these types of effects will be looked at in more detail. That is a much more challenging and difficult discipline, but it's an active area of research even now. So you're going to find that, I think, very interesting, but we have a long way to go before we get to critical phenomena. That's all I'm going to say about phase transitions. And in the next lecture, we're going to go back to fundamental classical statistical mechanics and Boltzmann statistics. Thank you.